We are at Clausius and the Clapeyron equation. Remember, you do not have to memorize this. P, and then you have your vapor pressure. So at temperature 1 over temperature 2 is equal to delta H. So the enthalpy of vaporization, which we said was your boiling, over R times the difference of 1 over T2 minus 1 over T1. Temperature, remember, has to be in kelvins, and then your R is the 8.314 is what you have to use. So let's do a problem. So vapor pressure of water at 25 degrees Celsius is 23.8 torr. And the heat of vaporization of water at 25 is 43.9 kilojoules per mole. Calculate the vapor pressure of water at 65 degrees Celsius. So T1 is 25 degrees Celsius. P1 is 23.8 torr. T2, 65 degrees Celsius. And P2 is what we're looking for. We know that delta H is 43.9 kilojoules per mole. And R is 8.314 joules per mole. Okay. So what we do is we just start plugging in. So ln of P1 over P2 is equal to, so we have kilojoules and we have joules. So let's turn our kilojoules into joules. So we have 43,900 joules per mole. And that is over our R, which is 8.314 joules per mole. Okay. And then we multiply that times 1 over T2 is 273 minus 60. Oh, sorry. We have 65 degrees Celsius, so that is, add 273 to that. What is that? 273. What? 338 minus 1 over 25 is 298 Kelvin. And solve that for me. Anybody get 193.7? So 193.7, and our unit is torr. I think you have a couple of those on that homework from yesterday. Questions over that? All right, so let's move on. So here's a heating curve for water. The question is, which would you predict should be larger for a given substance, the delta H of vaporization or the delta H of fusion, and why? So, yes. So you need to figure out where is fusion and where is vaporization. So here is your delta H of fusion, while here is your delta H of vaporization. So the largest one's going to be what? Delta H of the vaporization, and why is it larger? Because it has to overcome all the intermolecular forces that are present. Anyone have any questions over that? Okay, so solutions. There are different types of solutions. You see it could be, yes? I'm not going to say always, but I would say solutions come in different forms. You see you could have a solid and a solid for a solution. One for the solute and the solvents. You could have two liquids. Who would put vodka in antifreeze? That's just so weird.
Really good. You'd be surprised.
That is just weird. That is just such a weird combination.
Did you hear what Marcus said?
I did. And I'm ignoring it because I'm recording. So, now, next, we have different types of numbers that we can calculate. So, molarity is something back from pre-AP that you should remember. Moles of solute per liters of solution. We can get mass percent, which is going to be mass of your solute over the mass of your solution times 100. Mole fraction is going to be moles of A that you are interested in, whatever substance you're interested in, over the total moles of the solution. And then you have molality. And molality, the AP is not really concerned with. So you're not going to do any calculations with those, but just know that it exists. And that is moles of solute per kilogram of solvent. So we're going to go do some problems. So I said you need to have your calculator. So if you have 1 mole of 125 milliliters of solution, calculate the concentration of units of molarity. And remember, molarity is just a fancy word for concentration. So we have molarity is equal to 1 mole divided by 0.125 liters. .0 moles per liter, or if you don't want to put moles per liter, you could say 8.0 big M. You have 10 molar solution of sugar. What volume of this solution do you need to have 2 moles of sugar? So 10 is equal to 2 over X. Solve for X. To 3 sig figs, we get 0.200 liters, or 200 milliliters. And lastly, it says consider separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each in 250 milliliters of solution. Calculate the concentration of each solution in units of molarity. So first of all, if I have 100 grams of NaOH, I need to convert that to moles by using the molar mass. What is that? 2.
Should be like 41.
Huh?
Should be like 41.
41?
Well, because
100 divided by 40? 2.5? 2.5 moles. And then we're going to put that over 0.25 liters. And that gives me 10 molarity for NaOH. And then we go and do the same thing for KCl. So for KCl, we have 100 grams. And the molar mass is 46 grams per 1 mole. And what do we get here? What was it? 2 point what? Okay, KCl 74. 35 and 40. Oh, I don't know why I put 46. 74. Because I missed that 7. So 74.6 grams per 1 mole. And that is what? 1 point what? Thank you. I cannot hear him. I'm deaf. Moles. And now we do that over 0.250 liters. And we get 5.36. Big M for KCl. Okay, so let's do some mass percent. This is mass of your solute over mass of your solution. So what is the percent by mass concentration of glucose in a solution made by dissolving 5.5 grams of glucose in 78.2 grams of water? So my solute over my solvent plus my solute times 100. 6.57. So 6.6% glucose by mass. All right, mole fraction. So we're going to take the moles that we are interested in and put it over the total moles of the solution. So here we have a solution of phosphoric acid, and it was made by dissolving 8 grams of H3PO4 in 100 mils of water. Calculate mole fraction of H3PO4, assuming water has the density of 1 gram per mil. So the first thing I need to do is I need to convert my phosphoric acid to moles. So we take 8 grams of H3PO4 and multiply it by the molar mass of that, which is 98.0 grams. I get 0.0816 moles of H3PO4. Then we also have 100 milliliters of water, so we're going to assume that this is 100 grams of water. So we have 100 grams of water, and we need to convert that to moles. So 18.02 per 1 mole gives me 5.55 moles of water. And the mole fraction we care about is for H3PO4. So X, which is mole fraction for H3PO4, is equal to 0.0816 over the total number of moles. No, you do solve it.
0.0145.
So 0.0145. And that there's no units. Everybody good with that? I'm not sure if we did that in pre-EP last year. I think I ended up skipping it over it. Molality?
Yeah, that was fun.
So molality, just know it exists. We're not going to do any calculations. So let's talk about the process of dissolving. You need to know this. Let's start. So what happens is you separate the solute into its individual components. So the intermolecular forces in the solvent have to make room for the expanding solvent, and then you allow them to interact to form the solution. So if we look at this picture here, when the solute goes and it expands, we have a delta H, and that delta H is a positive. Okay. When we have the solvent, and the solvent is expanding, that is also a delta H that is positive. So first you expand your solute, and then the solvent starts to expand. Both of those are positive delta H's.
And that's because PV was and energy, right?
Huh?
He's talking about
Pervnert?
yeah, right?
What about it?
Because you're expanding, you're cooling it down temperature,
Oh.
right? Why else would that?
It takes energy to break those particles apart. So that's why it's a positive. Now, when you put these two together, what happens is we get a negative energy. Usually, it is negative energy when you put these two together. So when we end up adding all these delta H's together to get the delta H of our solution, you have a positive, usually a negative. So your delta H of your solution might be positive or might be negative, depending on what that difference is. And that explains it all over here. So your final solution is either going to be endo or exothermic, depending on what these values are for delta H. But usually 1 and 2 are endothermic, and 3 is exothermic. And then the delta H total of the solution can be either one, depending on that difference. You've seen this before? So we see here that if we're going up, then we're inputting energy. So if we go up this way, we have energy going in. If you're moving down, then you're putting out energy. So you see here you have a negative delta H, while here over on the other side you have a positive delta H. So this one is endo, exo, and this one is endo. So you have to be able to look at those graphs and see what's going on. Questions on that? You think they're going to go back to regular bell schedule?
It's lunches right now, so.
Well, I mean, at like the bell, when the bell rings, they'll go to 6. No, they still have to go to another lunch, don't they?
Yeah.
Okay. All right. So next, tell me, why does water and oil not mix? And you have to talk about delta H in this. Yes. So, what is water's polarity? Water is polar. Oil is nonpolar. So, what happens when you make a vinegar and oil? You put those together. What do? You shake it, shake it, shake it, shake it, and that mixes them, right? But what happens eventually? They separate out. So once separated, what happens is the water molecules are going to be more attracted to themselves. Okay? And so that's why it comes back together. And we don't put enough energy into it to overcome that intermolecular force so that those water molecules are no longer attracted to themselves. So we don't have enough energy in there to overcome it. So I'm just going to put here once separated. The water molecules are attracted to themselves than to the oil molecules. So,
Contactors and teachers, so we're about to ring a bell, moving from...
mixing doesn't happen. So mixing doesn't...
Wait, they're more attracted?
They're more attracted to themselves than to the oil molecules. Doesn't happen. Therefore, we got to take into account delta H. Therefore, it is not... energetically, is that a good word? Energy favorable. Huh? There's not enough energy to overcome those intermolecular forces. And so because there's not enough energy, then we're not going to have the mixing.
Wait, so what's not energetic?
The mixing of water and oil.
And that, it's the same thing. That's talking about H.
Delta H. We can't overcome delta H. Okay, so one factor, let's refocus, let's go. One factor that favors a process is the probability of the state when the solute and solvent are mixed. So remember that the universe favors disorder. So we have to think about the entropy in this case. universe favors disorder. And processes that require large amounts of energy aren't going to occur. So oil versus water, or oil plus water.
How does soap work?
Is that why like when an ocean happens on the water, it's just on top? Yeah, you just like mop it up. So basically, it's real.
Um,
That's why I can totally sense
I know we pound in your heads like dissolves like. Don't write that on your paper. Don't write it on paper for me. You need to actually explain in terms of the delta H of why a reaction occurs or not. Okay. So factors that affect your solubility is the structure effects, so the polarity. So what helps a solute in a solvent? You have to think about the polarity. You have to think about Henry's law and the temperature. And that goes all back to pre-AP. So structure effects, whether it's hydrophobic or hydrophilic, does it like water or does it not like water? Okay, so if you're hydrophobic, then those are going to be your nonpolar substances, and we are not going to dissolve in water, whereas if you're hydrophilic, two hydrophilics together are going to dissolve. Pressure is directly related to, or solubility is directly related to the amount of pressure. So if I increase my pressure, I increase my solubility of my gas. So if I increase pressure, you increase your gas solubility. So think of this as your soda that's been sitting out. The gas has already come out because it's no longer sealed. So pressure effects are all for gases. Gases.
What about compressible liquids?
It's not really going to... The compressibility of a liquid is very... Okay. Here you see that temperature is different between our solids versus our gases. Usually our solids are more soluble in higher temperatures, whereas our gases become less soluble. And this is stated in the next slide. We're going to go ahead and right here where it says the solubilities of some substances decrease with increasing temperature. That's kind of really talking about gases, and it's stated down in that third portion. Is everybody good with that? And the last thing we're talking about are colligative properties. Yes?
So, do salts at high enough temperatures decrease in their solubility even if they would be solids at that temperature, or do they just bottom out?
Repeat the question.
Do salts
Salts. Okay.
at higher temperatures decrease at high enough temperatures, decrease in solubility, even if they would be liquids or solids at that temperature? No? No? because it goes through.
It's a good question.
And they could go back up.
Okay, Marcus. Colligative properties. We did not talk about this in pre-AP. We should have, but colligative properties are properties that depend on the number of molecules that are present in our solution. So, we don't care what the particle is. We just care if they are soluble in solution, and as long as they're not volatile. As long as they're not volatile solutes. So this is all dependent upon them not being volatile. So the things that are going to depend on the number of molecules in our solution are vapor pressure becomes lower. So if I have a solution of water, or not a solution, I have my water, okay, and here's my water molecules. And I take, I don't know, let's take sodium phosphate and take a 1 molar solution of it, and we put it in there. Now what happens is we end up getting the following. We end up getting some NAs in here. We get 3 NAs. And we get 1 PO4. So how many ions did we put in there into that solution? We put 4 ions in there. So we have more particles in this solution. So since we have those more particles in the solution, we're going to have, the vapor pressure is going to decrease. Why? Why does the vapor pressure decrease? Why do these particles not want to go out of solution? You have to look at me when you talk. Sorry, I'm just...
There's more room made.
More room...
Made by, what was it? By the first of
Oh, for the expansion? Okay, I see that. But how is it going to be easy for those water molecules to come out of solution? Vapor pressure lowering. That means those water molecules are not coming out. So why are those water molecules not coming out? Why is our vapor pressure lower? Okay, so when we put those ions in there, what we have is we have less, those are impeding, those ions impede the ability for those other molecules to come out of solution. Okay. So now we have more intermolecular forces going on in there, and that's going to keep our vapor pressure low. Now let's take the same solution and start boiling it. When we start boiling the solution, then when we boil water, it's going to be at, say, 100 degrees Celsius. Now if we put something else in there, what happens is it's going to take that whole thing longer or more temperature for it to boil. So it's going to maybe boil at 110 rather than 100. Again, why is it going to take more for that water to boil? Because it's harder to overcome those intermolecular forces. It's being impeded by those extra ions that are in the solution. And same thing with freezing point. Freezing point goes down because for those water molecules to come together and to freeze, right, to have that hydrogen bond, we can't have that hydrogen bonding. It's harder to do that hydrogen bonding when you have other molecules in the way. Okay, so those water molecules impede the vapor pressure of the boiling point and the freezing point. That is why they put salt, because it decreases the pressure, the freezing point of water. That's why we put antifreeze in our cars rather than water in the radiator, because it takes our range of water's boiling point and freezing point and it expands it. We can expand that range because we've added more particles within the solution. Okay? Any questions on that? All right, that's it. Test is supposed to be tomorrow. I'm going to give you guys a test review for those of you who aren't going to be here, and then I'm just going to move the test to Monday. I know it's after holiday, but we'll do it Monday.